The nice summary of George Reed of basically the Dungy convection cycle has been with us for a long time. There may be a few detractors out there who don't believe in it, but it's been very useful in organizing our thinking about why there's convection, why there are storms, where the energy comes from, why there are substorms, and so on. In this sort of interim period of 40 years since George Reed's talk here, a lot has accumulated from satellites and ground-based observations, climatology in effect, that actually paints a somewhat more complicated picture of the Dungy, the basic Dungy convection cycle. And there's some fairly robust effects that come out of the climatology. And in fact, in this conference already, there's been some allusion to the inference of dawn-dusk asymmetries and ionospheric outflows, for example. And a subtopic of this talk is what causes that dawn-dusk asymmetry. So I'm going to scroll through some climatology fairly quickly just to give you a sense of how robust the effect that I want to talk about is. Go through quickly an early result on the effect of ionospheric conductance on ionospheric convection, and then use the tool that I'm going to use is global simulations and do some controlled experiments. One of the problems we have in our science is that we're dealing with this expansive environment, and we can't really do controlled experiments. We take what nature gives us and we try to understand what's happening. And in global simulations, we have the opportunity to actually control experiments and try to tease out cause and effect. So I'll go on and talk about the implications of ultimately ionospheric Hall conductance on night-side reconnection fast flows in Earth's plasma sheet. Okay, so some climatology looking at things from the polar ionospheric perspective. There are a number of effects here. Downward Alphanic pointing flux. This is bandpass filtered Alphanic pointing flux inferred from the polar satellite, projected down to the ionosphere. Broadband electron power, 10 years of data, statistical model of Pat Newell et al. Of electron. These are basically superthermal electrons, not inverted V electrons. Pat calls it broadband electrons. Precipitation. Jim Burt showed yesterday this same plot of outflowing O+, and then in the thermosphere, if you subtract off measurements 1 year of data, statistical averages again, of thermospheric density at 400 kilometers, subtract off the MSIS 90, you see a pattern like this. And one feature that you see in all of this is that in the pre-midnight sector, the intensity is greatest. Okay. One of the ways that we got on to thinking about this problem was one of my graduate students, now a postdoc, Ben Zhang, started looking at the LFM global simulations and found when he started averaging the results, extracting the Alphanic pointing flux and averaging the results in the same way that Keiling did from the polar data up here, similar pattern emerged from the global simulation. So when you see that, the first thing that ought to come to everybody's mind is, okay, so now we have this tool that's giving the same result, it seems like. So can we use it to try and figure out why we see this pattern at low altitude in these various quantities? And I don't have time to go through the causal connections between all of these various patterns that I've shown up here, but we're actually using the model to make predictions like this in broadband electron power, thermospheric mass density, and so on, outflows. Okay, climatology of high latitude convection. Rod showed some plots yesterday from Dan Weimer, and Rod's absolutely correct that when you look at the state of the ionosphere on an instantaneous or an event basis, it really doesn't look like this. But yet this is the climatology that we have. If we look at things in aggregate, then we start to see things like this. And there are two features here that are persistent that I'd like to call your attention to. So one, there's a clockwise rotation of the ionospheric convection pattern here. This is for zero dipole tilt, and the Weimer model requires these input conditions. And as inferred by the difference in the potential maximum in the dusk cell versus the potential minimum in the dawn cell, there's more magnetic flux circulating in the dusk cell than the dawn cell. Okay, so there's this persistent asymmetry, and you can put different conditions into the Weimer model, and you see that these effects persist for, this is for dipole tilt characteristic of summer, equinox, winter. You can change the input IMF here. These are all for minus 5 nanotesla in the IMF across the bottom here. All zero dipole tilt, minus 2, minus 5, and minus 10. And you see that this rotation persists, and the asymmetry in the circulation in dusk relative to dawn. And I'll say, if you put it in IMF BY, it's more complicated, but the same effects are still there, moderated to some extent by IMF BY. Okay, now let's take a look at the climatology of plasma sheet bulk flows. From geotail averages over a 5-year period, what you see is that, and of course this is the dusk or pre-midnight sector and post-midnight sector over here, tailward out to minus 30 RE, and you see that on average the flows in the plasma sheet are larger in the pre-midnight sector. If you ask where the flows are the largest, so in this paper by Raj et al., based on when the 17 perigee passes, and the passes are indicated in gray here, where data could have been acquired. And if you ask for flow velocities greater than 250 kilometers per second when the plasma beta is greater than 1, to indicate that you are in the neutral sheet, then you find that most of the fast flows occur in the pre-midnight sector here. Another analysis, a much longer baseline, using 3 different satellites, data corrected for the aberration of the Earth's orbit relative to the sun, and so on, and you find similarly preponderance of the fast flows over in the pre-midnight sector. From a recent paper by Bob McFerrin from Themis, going out only to about 10 RE here, blue indicating earthward flows, red indicating tailward flows. Here's the probability distribution as a function of local time, again, pre-midnight preponderance of these fast flows. Okay, coming back down to the ionosphere now, we know that these fast flow bursts have signatures in the ionosphere. They look something like this. We see a very disturbed polar cap, poleward boundary intensifications along here. This is a fairly slow cadence image from the polar viz camera. And if we look at the statistics of the poleward boundary intensifications, which was done by Nishimura et al. At UCLA, you see in the poleward boundary intensifications concentrated at relatively high latitudes in the pre-midnight sector, and those are associated, we know, with fast flow bursts in the magnetotail. Okay, now to try and get some organization into the cause of this asymmetry that we're seeing here, I'm going to go back to a paper by Yasuhira, Greenwald, and Akasofu, 1983. And they asked a fairly simple question, and with a really simple model, and sometimes simple models have a lot of insight in them. They don't have all the reality of the problem, but they're very useful in that regard. So they solved this basic equation for the ionosphere. This is basically the divergence of the height integrated perpendicular current in the ionosphere, and that's equal to the height integrated divergence of the parallel current which is just J parallel in this case, and making the electrostatic assumption. And they assumed a simple model here. So red indicates the baseline conductance distribution, different for Pedersen and Hall. And then they had a uniform in local time band in which they varied the value of the conductance in this band. And then they assumed a distribution of field line currents, region 1 and region 2, like sheet currents on the poleward border of these conductance enhancements. It looks like this. And then they solve the equation, piecewise continuous, solve it in the polar cap, solve it in the auroral band, solve it at low latitudes, and then enforce the continuity conditions from Maxwell's equations. And for different variations of the step in conductance, so 1 means that there's no enhancement in the conductance band relative to background. So they did a number of cases here. So this is the case where there's no variation in the band relative to the background, and it's the nice symmetric convection pattern that we often draw. And then with a step of 2 in the band, in the Pedersen and Hall conductance here, you start to see a rotation and further rotation here and further rotation here as the conductance goes up. And this is for each of these cases. And the conclusion that you get from this analysis is that it's the meridional gradient in the Hall conductance, not the azimuthal gradient, but the meridional gradient in the Hall conductance that's causing this rotation. In fact, if you keep the Pedersen conductance uniform and put a step band in the Hall conductance, you get a rotation. If you keep the Hall conductance uniform everywhere and just put a step band in the Pedersen conductance, you don't get the rotation. It's the Hall conductance that's doing that. And a simple picture to illustrate, it doesn't have all the complexity of the of solving this problem in cylindrical geometry, like you saw in the previous plot. But if you suppose this is the polar cap here, this is the day side auroral band, night side auroral band, high conductance in this band, and with polar cap flow from right to left through this region. And of course the Hall currents go in just the opposite direction of the E cross B drift. And so you have a Hall current that's flowing in this direction. And there must be a divergence in the Hall current at the divergence or gradients in the Hall conductance, because here, for the same electric field in these two regions, the conductance is higher in the band than it is in the polar cap, and so therefore there's a divergence in the Hall current at this discontinuity. And of course that can't persist. Charge will build up and something is going to happen afterwards. There are 2 ways to relieve that situation. One is to just divert that excess Hall current into a field line current, and that solves the problem. No longer a divergence. That's one way to do it. Another way to do it is to rotate the electric field. And so what I've done here is just rotate the vectors that appear in the Pedersen and Hall currents that appear up here, so that the Hall current is completely continuous across here now. And there will be a divergence. You can't guarantee necessarily that the Pedersen current will be divergence free, and that will go into field line currents if that happens. But and so what you see is that in effect you can think about this process, this case with divergence going to this case being one in which there's a rotation of the electric field and rotation of the convection pattern. In fact, in the polar cap, this is a clockwise rotation of the convection pattern. That's the basic effect that Yasuhiro et al. Were discussing. Okay, so the work, the kernel of this work, is actually started as a master's thesis by Ryan Smith at Dartmouth, and with a lot of help from the people that appeared on the first slide, including Gerhard Herendell when he spent a fall at Dartmouth, and so a lot of ideas and so on came out of this collaboration. And Ryan went through and did a whole series of controlled numerical experiments using the LFM simulation model. One fluid, so there's no outflow. geomagnetic field, there's a point dipole at x equals 0. It's a large cylindrical domain, upstream boundary condition at 30 RE, low altitude boundary condition at 2 RE. It solves the same equation for the ionosphere. And sigma is determined, well, there's a precipitation model in the LFM simulation model that includes ionization due to both precipitation and EUV. But some of the experiments, in fact, most of the experiments that Ryan did were actually controlled and contrived for the conductance. So what I'm going to do is I'm going to take you through and show you some of the results of what the ionospheric convection pattern looks like in these simulations, and then go out into the plasma sheet and see what the implications are for the plasma sheet. Okay, so here we have a uniform conductance, no asymmetry. In this case, we have a step band in the Hall conductance, uniform Pedersen conductance. So this is a very contrived, azimuthally uniform in local time, but a gradient in the conductance in the meridional direction. And we're starting to see here a rotation, but what we see is that the flux circulation in the dawn cell is actually less than in the dust cells, less than in the dawn cell for this contrived simulation. Okay, so a whole series of other ones. This is the same one that I just showed you, and this is similar to the one that I just showed you on the previous plot, a little bit different conductances. What you see here is the empirical model for conductance from LFM, including the EUV contribution, which gives this day to night almost linear gradient in the, well, not linear, but gradient in the conductance, and then this more irregular band, auroral band here, is due to the dynamic causal empirical precipitation model. And then here you have a simulation in which the EUV contribution to the conductance only is included in the simulation, no auroral precipitation. And what you see is actually the EUV contribution causes a rotation in the opposite direction, counterclockwise moderately, but gives a very significant asymmetry in the flux circulation in dusk relative to dawn. And so you put this case together and this case together, and you get this situation up here. And the EUV contribution wins out in the flux circulation, but the sigma band enhancement wins out in terms of the rotation in this case. And then here's an interesting experiment which nature absolutely will not do for you. And this is one where you dig a hole in the Hall conductance in the auroral region. So this is not an auroral enhancement. This is an auroral depletion in the Hall conductance. And what you can see here is that the rotation now goes in the opposite direction. And the flux circulation relative to the case with the sigma band enhancement is just the opposite. Okay, so I think these experiments show fairly clearly how important the Hall conductance is in controlling that pattern that we see in the ionosphere and the flux circulation in the ionosphere. What does it mean for the magnetosphere? Okay, so now we go into the plasma sheet, and these are the same 6 cases here. How am I doing, Rod, on time? Till 20? Okay, great. So this is the uniform case, and what's shown here, color-coded, the flow velocities in the plasma sheet. The arrows indicate the direction, so the arrows, and so anyway, there are 2 different ways of viewing it. And so for the uniform conductance case, it's symmetric across the plasma sheet. The red line here is, by the way, these are all of these simulations are for steady, dead steady solar wind conditions, BZ equal -5 nanotesla, Vx, the solar wind velocity, 400 kilometers per second, no By in the solar wind or Bx, no Vy or Vz. So in other words, the solar wind is such that there's nothing to give asymmetry in the system. And so in the case where the conductance is uniform, things are fairly symmetric. For the empirical conductance model, we see that there's an enhancement in the fast flows, or the flows are larger in the pre-midnight sector than in the post-midnight sector. And these are these various cases again. And I would just point out the contrast between this case and this case. This is the case where we had the depletion in the auroral conductance band, and now the fast flows have moved over to the dawn side or the post-midnight side, where they don't typically appear, at least statistically. Now, we did some more careful simulations, higher resolution, to take some measurements. Again, this is the BZ equals 0 contour in the equatorial plane, which is a pretty good indicator of the X-line. And so there are a number of fiducial points here. We've measured the rotation by drawing a line between the potential minimum and maximum and asking what is the angle relative to the horizontal for each of these cases, and this gives the angle up here. And then the dots, circle X, that appears in these plots is where the zero potential contour in the ionosphere intersects the mapped X-line from the plasma sheet down to the ionosphere. That's what this white line is in the ionosphere here. And then once we find these points in the ionosphere, we map them back out to the X-line in the equatorial magnetosphere to find out where the zero offs, or the zero baseline is, and the potential and the reconnection potential. And we're actually going to integrate the reconnection potential along this X-line and to find the asymmetry in the reconnection potential that goes with these various cases here. And you can see the asymmetry in the fast flows, again, for the depletion case and the causal. These simulations, 1 hour average states that I'm showing here, and we did some up-down initially just to get the system to churn, to populate the magnetosphere, to lose some of the initial memory in the system. To measure the reconnection rate, there are a couple of different ways you can do it. You can just go to the X-line and integrate the electric field along the X-line. The other way is you can go out to some fiducial surface far away from the activity down here and actually calculate the amount of flux that crosses the separator line. And those two measures should be the same. And I guess I won't go into this in too much detail. But okay, thank you. What I'm going to show you is a plot where we just integrated along this X-line here. And so this is for the three cases that you saw for the higher resolution runs there, the uniform in black, the causal in blue, and the depleted. And the ratios of the dawn, dusk to dawn potentials in each of these three cases along that X-line is exactly the same, well, within some numerical errors of what the ratio is in the ionosphere as measured by the dawn and dusk potential minimum and maximum. Okay, so conclusions, and if there are no questions, I have a couple of movies to show, or if there's extra time to illustrate the point more vividly. But the effects of meridional gradients and ionospheric Hall conductance. So with a polar cap to night side auroral zone gradient. So this is on the night side going from the polar cap into the auroral zone. That gradient, as best we can tell, is what causes the rotation in the polar convection in the clockwise direction for normal type of gradient. And it moves the plasma sheet fast flows toward the pre-midnight sector. The day side to night side gradient, for example, that's associated with EUV ionization, rotates polar convection counterclockwise and enhances the dusk side reconnection potential. So this gradient is what appears to be responsible for the asymmetry in the circulation in potential, as opposed to a simple rotation. And leads to pre-midnight reconnection exhaust flows that become more bursty as a consequence. The thing that's really curious about these results to me is that there's, at least at large scales, there's little ionospheric Hall current that's diverted into field line current. Most of the Hall current seems to be diverting into Pedersen current, which is associated with this rotation. Why does that occur? We don't really have an answer for that. There's been some work, Barbosa in the 80s, and most recently by Ahmed et al., making some very limiting assumptions that suggest that it may have something to do with the minimum dissipation state. The system wants to go that way because it minimizes the dissipation. It's not clear why it would want to do that. But it seems like some interesting area for additional research into the causes of these effects. Okay, thank you.
So we have time for a few questions. Comments? Tom?
Your rotation of, excuse me, the rotation of the convection pattern due to the divergence of the Hall current without creating a field line current.
Right.
That your last bullet there. That's highly reminiscent of the what we used to call a cowling channel.
Yes, right, indeed.
Where the absence of the Birkeland current is more or less assumed. Is there anything to that similarity?
It is. It's essentially that effect, right. I just didn't use those words, but you're right. Thank you.
I had just two very short observations. Very, very nice study. The first is in the spirit of going after our favorite journals and their referees and editors. For a long time, it's been very clear that plasma sheet flux ropes, which of course are produced by the same X lines that produce or drive the convection that you were talking about, they have a very, very pronounced preference for forming in the pre-midnight region, just as everything you did showed. It was interesting. It's actually one of the more difficult times I've ever had with referees in the last 10 years.
You mean they didn't believe it was pre-midnight, or?
They basically, you know, lots of different data sets, a lot of different noise. The most recent studies that you were citing, I think, finally put it to rest just by the sheer volume of the data that shows it. After all of us know the asymmetries in the auroras, which you put into your model, basically, and it wasn't very surprising that the things favor that side of the tail. Second comment, also in another spirit of the meeting, I wanted to comment upon a generation gap. And it was kind of alluded to or exhibited in Bob McFerrin's talk. And that is, I would just call attention to the fact that back during the IC1 and 2 era, early in ISTP, when certain individuals, I'm not looking at Dan Baker either, were involved in those debates about you know, how important reconnection was for driving the Dungy cycle, and it inevitably got down to where reconnection occurred. There was a huge amount of discussion, or the discussion usually centered on 15 to 20 RE down the tail. And whenever I think of diagrams like you were showing, that's where I tend to put the X line. I have noticed, though, that today the students that I work with who are analyzing the Themis data, they quite correctly, for the current era, have the X line typically at 25 to 35 RE down the tail. And it absolutely is true, and it is because of this anomalously weak solar cycle, incredibly weak interplanetary magnetic fields, and the magnetosphere is just not being as stressed, it's not being driven as hard, and the X lines are tending to form farther down the tail. It's just rather interesting when you ask people to go pick your typical numbers and put them on the board and have a discussion. Today's students will put an IMF of 3 nanoteslas. We'll all put 6 or 8 nanoteslas, and we'll put the X lines much closer to the Earth than farther down. I don't know what it'll be 40 years from now, of course.
Is that the geotail studied where the X line is, and it's very rarely at 20 RE. It's mostly much further down the tail. So that's kind of the inner edge of it. That's the closest edge to the Earth.